Welcome to this lecture series on artificial intelligence. We're going to be focusing on neural networks and machine learning. I'd like to begin with a quick introduction. So let's answer a couple of questions. First is, what is artificial intelligence, or simulated intelligence, which is the term that I prefer? It's a field of study tasked with the development of methods and algorithms that enable machines to observe the environment, either directly via some sort of sensor or indirectly if that's data that we're supplying, learn from these observations and the patterns embedded within them, as well as make intelligent decisions to optimally solve a variety of different complex and potentially abstract problems. In short, we seek to develop hardware and software with the observation, intuition, and decision-making capabilities of a human. Now, what about machine learning? Machine learning is a field of study within AI, tasked with the development of generally iterative and statistical methods or algorithms that accept training data, learn relevant patterns and relationships from that training data, as well as allow us to generalize those relationships or apply them to new cases that are not part of the training data set. We may visualize machine learning like repeatedly shooting a free throw. Right? We shoot the free throw over and over again. Every time we miss, we make a small adjustment until we're able to make the free throw consistently. After we're able to do that, and we could call that convergence, we no longer need to continue the learning algorithm or the machine learning algorithm. Generally, an artificial neural network provides the mathematical structure to which machine learning is applied. However, there are some unsupervised methods like K-means clustering that don't require the neural network. So what is an artificial neural network? It's an interconnected group of processing nodes based on a drastically simplified model of the human brain or of a single neuron within the brain. Each node accepts several input values. So we can imagine several inputs coming into a node, which I'm just going to represent by this circle here. Now, these could be direct inputs from the environment or outputs generated by other nodes, right? Because one node, the output of that, can act as the input to another. It applies a weight to each input or each state. So we're going to apply a weight. We're going to scale each one of these values. Machine learning is generally tasked with defining these weights optimally. It then sums the weighted values to aggregate all the incoming information and applies some sort of an activation function in order to process the weighted summed input and generate the output, right? Generates a single scalar value output. And then for some neurons, these outputs will represent the desired final result. And that would be the case where a neuron is in the output layer. So let's take a look at this very simple neural network. I don't want to go into too much detail here because we are going to address that in depth in the next module. So what we have are two observed inputs, x superscript 1 and x superscript 2. To each one of the inputs, we apply a scaling factor. This one is called w subscript 1 superscript 3, or the synapse weight between the value at neuron 1 and the value being supplied to neuron number 3. This one is denoted as W subscript 2 superscript 3 because it represents the weight between neurons 2 and 3. So then we have our scaled values. We sum those together to aggregate all that information into a single value, which we generally call H. We apply to that some sort of an activation function, and then we generate a new state. The output of one neuron serves as the input for another. We also have a second neuron here. This one accepts one value from the previous stage as well as one from the input layer. We apply the synapse weights. We sum those values together, apply an activation function, and then we get our final output Y. Again, this is just a preview. We're going to dive into the details of how this works in more detail in the next module. So let's talk about the process of building a very simple AI, or a very simple neural network. The first thing we have to do is design the structure of our neural network, one that we believe has sufficient complexity to approximate the desired patterns and relationships that are present in the data. Next, we need to acquire training data, which represents the ideal relationships between the inputs and the outputs that we wish to approximate. So let's say we're working on a handwriting recognition neural network, then our training data would have really two columns. Okay, one column would contain the visual representation of the handwritten letters, and the next column would tell us exactly what letter that is supposed to be. So training data, one important, perhaps the most important characteristic, is that it must define the ideal outputs associated with the inputs. If we input this script letter that looks like this, we know that ideally that should be recognized as a Y. Next, we have to apply machine learning to optimally define the synapse weights such that for a given input, given input from the training data set, the ideal output y ideal, and that generated by the neural network, which I'm going to call y sub calc, are the same. And then once we've reached convergence, we can start to perform estimation. What we can do is we can look at what results the neural network generates for non-training data. So what are some advantages of neural networks and machine learning? What's the motivation here? One is flexibility and versatility. The structure of a neural network is generic for many different problems, and as is the application of machine learning. We may develop, therefore, hardware. One great example is the hardware that NVIDIA has developed, one that's highly optimized to perform the necessary calculations, the ones associated with neural networks and machine learning, and not general or not specific to multiple different applications. Another advantage is the ability to learn. Through learning, the neural network allows us to mimic complex, open-ended, and highly nonlinear relationships that cannot be practically represented in a closed form. So, for example, let's say we were tasked with creating an equation to detect a human face at any angle. That's highly impractical and would most realistically be impossible. Another advantage is the pattern recognition capability. So neural networks employing machine learning are well suited for identifying patterns and relationships within data, even when we really don't have any idea of what the form of that pattern or those relationships are going to be. And this makes them ideal for applications such as image recognition, face recognition, speech processing, or natural language processing. Now, another advantage, another motivation would be fast computation. Once trained, a neural network, when it's predicting the output associated with a given input set, is very fast, and that speed is largely independent of the system size and complexity, right? The computation time for the forward propagation, so we're assuming that machine learning has been completed. Most of the effort is going to fall on the machine learning end, okay? The computation time for the forward propagation is dependent on the number of layers and the propagation delay through those layers, and those values are generally pretty small. So this is a drastic advantage, or this is drastically advantageous over non-linear optimization methods, for example, something like Newton-Raphson, that require matrix inversion and could be applied to similar problems. Now, those non-linear optimization methods have computation times that grow greater than linearly, with those that employ large matrix inversion generally growing at a cubed rate. So that marks the end of this first module on artificial intelligence. It serves as a pretty short introduction, and I think it did a good job of achieving a couple of discrete goals. First, it defined some terminology that we must be familiar with to understand later modules. It also makes us familiar with at least the very basic structure of an artificial neural network that we can build upon later, and most importantly, like I said a second ago, it prepares us for those later modules, which are going to dive deeper into the topic of artificial neural networks and machine learning, etc., as we move on to the next modules.